Evening is 5 o'clock on Thursday. Time for some Calc 2. We're a little small class size at the moment. We'll see if we get some more joiners as we go along. Okay, so like we talked about, today we're going to be finishing up Module 1, which means the Module 1 quiz is coming up. I'll talk a little bit about that at the end, just in the last couple minutes of class, point out a couple things to help you prepare. So we'll address that a little bit later. Let's dive into the content for today. So today's topic is improper integrals. There's a couple interesting things going on with improper integrals, and these do have a lot of practical implications. They're used actually quite a bit in statistics with probability densities, but they do come up anytime that we have a situation where something is infinite. And that could be where our limit is infinite or our integral is infinite. And we still might be able to make value of that if it converges, okay? And I'm going to talk a little bit more about that idea of convergence as we go along. We're going to see that's going to come up, this idea of improper integrals is going to come up again later this semester, sometime after the midterm. So my recommendation is get this down now. This idea of improper integral, we're going to look at something called the comparison test. Get it down now, and the idea of convergence and divergence, because when we come to it in I guess it would be Module 4, then you're going to be a little bit more comfortable with those ideas, okay? So I'm actually glad this section is on a Thursday, because this is our long break for the next class, so you can spend a lot of, some time over the weekend really getting this stuff down. All right, so improper integrals. Let's talk a little bit about this. Oh, I'm going to be using some slides. If you didn't see it, if you didn't get the link, it was in the invite, but I'll also throw it here in chat. So in case you want to follow along, here's the PowerPoint. So far in computing definite integrals, we've been on the interval a to b. We've assumed our interval was finite length and our function was continuous. We talked a little bit about this last time when I was just kind of giving a little bit of motivation for numerical integration. Life isn't made up of continuous functions, and it's not always made up of finite intervals. So we need to be able to accommodate those. Numerical integration was the way we dealt with it on Tuesday. Now we're going to talk about improper integrals. So sometimes we'll have an integral that's on an unbounded interval. In other words, one or both of the limits are infinity. We also may have a case where the function that we're taking the integral of is not continuous on our interval, but its definite integral may still exist. So those are going to be the two cases we're going to look at. These are what are called improper integrals. The first case is very, very easy to identify, and that's when the limit of integration is infinite. You're going to see something like this. Notice that upper limit is infinity. So when one of the limits is, or both the limits are infinite, it'll be very obvious in the problem. So the question becomes, can we calculate this? Now that we know we have an improper integral, can we calculate this? So let's talk a little bit about how we do this. Oh, shoot. For some reason, my tablet has stopped working. Give me 1 second. Of course. Okay, I got a backup tablet. Give me just 1 second. Sorry, guys. Let me try reconnecting. There we go. All right, sorry, guys. I thought it was working before class, and it wasn't. Okay, it's working now. 1 to infinity. of 1 over x squared dx. All right, we have a process by which we do this. The first thing we do with an improper integral is make it into a proper integral. So we're going to go from 1, instead of 1 to infinity, we're going to go 1 to b of 1 over x squared. But remember, we're doing an antiderivative. We like to write it as x to the minus 2. So let's just do that all in one step. Now, right now, these aren't actually exactly equal. So to make those equal, what we're going to do is we're going to take the limit as b goes to infinity. And now we haven't changed anything from our original. But here's what the reason we do this is now right here, this part is just a definite interval. Okay, so we're gonna not worry about the limit for right now. So limit as b goes to infinity. We're just gonna focus on this. All right. So we go into fundamental theorem mode, which is take the antiderivative. So the antiderivative of x to the negative 2, increase the exponent by 1, divide by the new exponent from 1 to b. All right. I'm gonna just, that negative, you can write it out front, whatever, you can actually even pull it out in front of the limit if you want. But what we have is limit as b goes to infinity of negative. And if you want, you can rewrite this as a rational expression. X to the negative 1 is 1 over x from 1 to b. Now, right now, again, we're not even focusing on the limit, but we do need to write it in every case to make it equal. You know, if you want to use quotations or something so you don't have to write it every time, that's fine. But technically, we want to write limit as b goes to infinity until we've actually taken the limit to make each line equal. So again, limit's still there. We're not dealing with it yet. We will soon. And now we finish off our fundamental theorem. Plug in my upper limit, so minus 1 over b, minus, plug in our lower limit, negative 1 over 1. All right, so we have the limit as b goes to infinity of negative 1 over b. That 1 over 1 is 1. We've got minus and negative, so plus 1. The constant this doesn't depend on b. So if we want, we can actually just say, oh, really all we want to calculate is limit as b goes to infinity of negative 1 over b, and then we're going to add 1 to whatever that is. So this is the limit we have to calculate. So we are going to be calculating limits. This isn't going to be the only time we calculate limits this semester. So if you do need some practice with limits, make sure you get it, whether it's from tutoring or from some YouTube videos or some of your old notes. Now, a couple of different ways we can approach this limit. First way is analytically. Think about what's happening. The numerator is going to stay 1, and the denominator is going to go to infinity. It'll go, and then we're going to make it negative. But think about what that means. You know, 1/10, 1/100, 1/1000, 1/1,000,000, 1/10,000,000, 1 billion. What is that getting closer and closer to as b goes to infinity? Oh, just this part here. Yes, good, Mark. Yeah, I know you were a step ahead of me. Good job. It's going to go to 0. Okay, let's say we didn't know that. Guys, you can use a graph to help you out. Put it up here in Desmos. Graph the function. So here I'll use x, y equals negative 1 over x. Oh, too many equal signs, excuse me. Remember what we're doing. B is going to infinity, and now we can see real clearly, oh yeah, even if I zoom out, as we go to infinity, the function is going to 0. So that limit goes to 0, and like Mark said, plus 1. This equals 1. And so that is the answer to our improper integral. Questions about calculating this? So here's what I want you to take from this, guys. Calculating an improper integral is one thing you've already been doing. It's calculating a definite interval. You know, if we ignore the limit for just a second, all I did over here on the right-hand part, take the antiderivative, plug in my limits, calculate the definite integral. So that's one, and that's something we've already been doing. So that's nothing new. And then you have to take the limit after you've calculated your integral. Okay? So we haven't done limits in here yet, but you've done them in Calc 1. And like I said, you're going to get some more practice in this. So we get 1. Let's talk about what that means. This is just the stuff that we did. And so what we say is the integral of 1 to infinity of 1 over x squared dx actually converges to 1. So if we can calculate the improper integral, it is what we call it convergent. And if it converges for an improper integral, if we calculated it, it actually converges to that number. Now, later in a little bit, we're going to look at something called the comparison test that just tests for convergence. It doesn't test what it converges to. So just for right now, just say, okay, well, if we calculated the improper integral, we got a number, it's convergent. Okay. So here's our definition of an improper integral. You don't need to know the formal definition. What you need to know is how to calculate, which we just did. And again, I can't stress this enough. You guys know how to calculate definite integrals. The only thing we're adding to it is a limit. Now, once we get to this point right here where we had to take the limit, if that limit exists like it did in this case, then we say that the improper integral converges. If this limit does not exist, then we would say it diverges. All right. And let's look at a case. Let's look at a case where it diverges. All right. But questions at this point? Sorry about that. Okay, let's look at a case where it diverges, just to contrast for a contrast. All right, so very basic one, we'll go 1 to infinity of 1 over x dx. This is very similar to the one we just did. And we're going to follow basically the same steps. So limit as b goes to infinity of 1 to b of 1 over x. Let's go ahead and rewrite it. Actually, now let's not rewrite this one. Sometimes rewriting this one can actually throw us off. You can. It's not going to change what the antiderivative is. You'd have x to the negative 1. Well, if you try to do the power rule with that, you get x to the 0 over 0. Well, we can't divide by 0, so that's your hint. This one doesn't get done with the power rule. What's the antiderivative of 1 over x?
ln of x.
Very nice, John. ln of, and now we're on the interval from 1 to b, and b is 1 to infinity. So we're already on positive numbers, so we don't need an absolute value. It's not wrong if you put in an absolute value, but you don't need one. And we go from 1 to b. So now we have the limit as b goes to infinity of ln of b minus ln of 1. ln of 1 is 0. And so what we need to do is now we need to check this guy here. That's the limit we need to check. Once again, you can do this graphically where decimals go. Now this one, let's see. There's something you got to be careful about with the graph of ln of x. You don't have too much familiarity with it, so it's good that we're looking at it. Right now, if I look at ln of x, it looks like it might have a horizontal asymptote, okay? And if I zoom out, it kind of looks like it does. So you got to be careful with ln of x. It turns out, let's do this. If all we do is increase the x-axis, watch what happens. Notice that, okay, wait, actually it's not leveling off. And in fact, we're going to do that exact, we're going to add a 0 to that. Let me see. Yeah, this will be good enough. Watch what happens as I keep adding zeros to the x-axis. So what I'm doing is I'm stretching the x-axis, leaving the y-axis alone. Notice how it keeps getting higher? There is no upper bound on this thing. It just keeps going and going and going and going and going. So here's the thing about logarithms. Logs are increasing functions. They just increase at a decreasing rate. Okay, so you got to be a little bit careful because the graph can be a little tricky on that if you're not familiar with what's going on. So this actually goes to infinity. If you find your limit goes to infinity or does not exist, you're done. Your improper integral is divergent. All right. And don't worry, we're not worried about what it diverges to. We're just saying, hey, it diverges. It didn't, if it doesn't converge, it diverges. And divergent is really important in mathematics because that means it blows up. It means it's not well behaved. So the way I like to refer to convergence, think of convergence as like well behaved. Function goes to a number. It behaves very nicely. When something's divergent, it doesn't go to a number, it goes to infinity. And what happens when you try to do math with something that blows up is it blows up your whole problem. So a lot of times with numerical mathematics, some of the stuff we were talking about last time, convergence is a very, very big idea with that because we need things to be convergent to know that they're well behaved. Again, I'm stressing this obviously because we're doing convergence and divergence now, but also because in module 4, it's going to be almost all about convergence and divergence. So this idea will come up again. So the way you'll identify a divergent is if you go to calculate it, and when you go to calculate the limit either does not exist or goes to infinity, automatically divergent. Questions about this example or the idea of convergence and divergence? Okay. This doesn't happen a lot, but this, like I said, this can happen. You'll see functions like this in statistics where you're doing an integral from negative infinity to infinity. If that is to happen, what you would do to do this improper integral is you split it up into 2 separate improper integrals. Okay, and you do them both separately. So, if we were, let's see. So here's how I would treat this. And I'm not going to do an example of this, but let's just say we have one like this, right? So we got negative infinity to some number. C is some number. C can be any number we want. So you split it up at the place that's easiest. Maybe at 0 or 1, so maybe we split it at 0. And then f of x dx. And we're going to go from then 0 to infinity of f of x dx. And this we've already seen, right? Limit as b goes to infinity from 0 to b of f of x dx. We see if that converges or diverges. When it's the lower limit, a lot of times we use A. That's just a convention. Doesn't matter, guys. You can use any letter you want. Just don't use the variable that's in your integral. And over here, the only difference is that A is going to negative infinity. All right. So then what you do is you do two separate ones. You do your fundamental theorem of calculus on your integrals. You do the two limits, and both have to converge in order for the original to be convergent. So if let's just say in practice you're working on this and you find this first one is divergent, you don't have to check the second one. You already know the whole thing is divergent. But if you get the first one converges, you need to check the second one to see what it does. So if you get one where both limits are infinite, you have to check two separate improper integrals, but they either both have to converge for convergence, or if one of them diverges, the whole thing diverges. Okay. All right. Let's go to case number 2. We won't do as many of these, but these do show up. They don't come in often as often in practice. We're going to be a lot more interested with the unbounded interval. Sometimes the integrand can become infinite. All right, so in this case, the interval is finite, but the function that we're integrating is unbounded somewhere on the interval. So consider this guy here. All right, the problem is we can't divide by 0, so this is not continuous at 0. So let's talk about how we handle this. So 0 to 1, 1 over square root of x dx. All right, so once again, what we do is we replace the problem child with a letter. 0 is the problem, so we replace it with A. 1 is not the problem. Because we're going to be doing an antiderivative, we rewrite this as a power function, x to the minus 1/2 dx, and we're going to do a limit, but now the limit is no longer going to infinity. A is going to 0, and specifically it's going to 0 from the right. Let's talk about why that is. Right, here's our interval 0 to 1. Well, I took out 0, so we're going towards 0 from the right because our interval is in between 0 and 1. If 1 had been the problem child, we'd be looking at the limit as x approaches 1 from the left, or A approaches 1 from the left. Okay? So pretty much if it's the lower limit, it's going to be as A approaches 0 from the right. If it's the upper limit, it's going to be as B approaches it from the left. So it is a one-sided limit because we don't care what's going on this side. It's not inside our interval. Okay, same thing as before. Limit comes later. First thing we got to do, compute the definite interval. This is just a basic power rule. X to the 1/2 divided by our new exponents from A to 1. Let's clean that up a little bit, make it a little easier to look at. Oh, geez. Sorry. Limit as A goes to 0 from the right. Dividing by a fraction, we flip and multiply. You can leave it as x to the 1/2 or write it as square root of x. You know, we're going to get the same answer either way. All right. Now, plug in, and then our last step will be to evaluate the limits, see what happens. So 2 times square root of 1 minus square root of A. All right, square root of 1 is just that. It's square root of 1. The only thing that depends on A is this square root here. We could actually do it from this step. Now, doing limits at a point, just as a reminder, the first thing you always do is you plug in the value, and if you get a number, you're done. If you get something that's undefined, you're done. If you get an indeterminate form, which would be 0 over 0 or infinity over infinity, that's when either you need to do something like L'Hopital's rule factoring, some algebra, or look at the graph, okay? So you're going to get a little bit of practicing limits in this section, not a ton, but we are going to be, like I said, we're going to be doing some limits again in module 4, and in there will be some, we will use L'Hopital's rule on. I don't think you're going to run into any really bad limits in this section. But just as a reminder, you have all those tools for calculating limits. So the first thing we do is plug in 0 for a. We can take the square root of 0. So let's just do that. Square root of 1 is 1 minus square root of 0. Square root of 0 is 0. So we end up with 2 times 1, or 2. And so we can say that this improper integral converges to 2. All right. So that's when we have the integrand being discontinuous on an interval. All right. Just like with the last one, like this was easy because the endpoint was where it was discontinuous. If you have, let's look at just one real. We're not going to go through this entire example. Oh, sorry. Actually, questions on this before we go on. On this example, on the convergence idea, the limit. And as always, guys, if questions come up while I'm talking, feel free to interrupt me and ask. Turn on your mic or something in chat. I don't mind. Because we're not face to face, it's hard for me to tell when you have questions. So please don't worry about interrupting me. All right. So here's something that could happen. Let's say we had the integral of 1 over x squared minus 4 dx, and we wanted to do it from 0 to 4. Now, the reason I bring up this one, 2 and negative 2 make the denominator 0. 2 squared minus 4 is 0. Negative 2 squared minus 4 is 0. Negative 2 is not in our interval. So here, 2 is the problem child. Well, when that happens, what you do is you split it into 2. So 0 to 2 of 1 over x squared minus 4 dx plus 2 to 4 of 1 over x squared minus 4 dx. And then we do the 2 improper integrals separately. So this would be limit as b goes to 2 from the right, because we're coming from between 0 and 2 to 2. I know that's a lot of 2's in there. But hopefully you're seeing when we do from the right and from the left. If you're not, let me know. And then we look at this one. Limit as a goes to 2 from the left, from a to 4. It's not a 4. Of 1 over x squared minus 4 dx. So then we do both these proper integrals, improper integrals, and like before, both must converge for the whole thing to converge. If just one of them diverges, the whole thing diverges. Okay. We're not going to do these right now because there's other stuff I want to look at, but I just wanted to give you an example. Sure. The reason it's 2, the reason I decided to split it, the reason we have to split it at 2 is because 2 is what makes the denominator 0. So that's the point of discontinuity that is causing the issue. When we did this example earlier, 0 caused the issue because it's 1 over 0. Now, the way we decide from the right and from the left, on this one, this first one, our interval is from 0 to 2. So I only care what's going on between 0 and 2. Hence, I'm approaching to. Oh, I got that backwards, didn't I? My goodness. I'm approaching 2 from the left. Oh, geez. I'm glad you asked. So we're approaching 2 from the left. And here we're approaching 2 from the right, because here we're going from 2 to 4. I'm glad you had me do that. We only care about between 2 and 4, so we're approaching 2 from the right. So from plus, from minus. Questions about that? So if you're ever not sure, or you ever make a mistake like I just did, just draw the line graph and say, oh, I only care about 0 to 2, and I'm going, the limit's going to 2, so it's going to 2 from the left. All right, this is just the work for this one that we did. Okay. So so the definition again is if our improper integral exists, it converges, and it converges to that definite number. Otherwise, it diverges. So those are our two cases. Like I said, in here it's gonna be like almost 8 to 1, 9 to 1. You're gonna deal with infinite limits over an infinite integrand. But we need to be familiar with both because both are improper integrals. Questions about that? Yeah, no problem. So we're looking over, so we're going from 2 to 4 on the second one, which is our interval. Now, we don't want to conflate that with the limit, though. The limit is only concerned about what's going on at 2, because 2 creates a point of discontinuity. If this lower limit was 2.1, we have a proper integral, and we can just go about our business like normal. It's not really 4 approaching 2. It's just that we're going to be approaching 2 from inside our interval, and so hence from the right. The 4 just happens to be our upper limit. Does that make a little more sense? These are good clarification questions. Okay. So basically what we're doing is we're going to, our limit is going to 2 because 2 is what was causing the problem, but we're going to 2 from within our bounds. So we're coming from the right. We're going left, but we're coming from the right. And that's where the little plus comes from. Those are called one-sided limits. Other questions? All right. Now there's a second part to improper integrals. And it's the comparison of improper integrals. You saw this in the online lesson. This is what's called the comparison test. Once again, guys, this isn't going to be the last time you see the comparison test. It's going to come up again in module 4. So again, let's get this down now so that when it comes up later, we're familiar with it. All right, that should be your goal. Now, what happens here is sometimes we have improper integrals that are tough to do via anti-differentiation. We discussed that on Tuesday with our numerical integration, right? Well, we may still care whether they converge or diverge. So what we do is compare to a known integral who we already know converges or diverges. So for example, 1 to infinity of 1 over x squared plus 2x minus plus 3 dx, okay? This is not as easy as the one that we worked earlier, which was this one. But we know that these should behave similarly because 1 over x squared and x squared is the lead term. So what we're going to do is use something called the comparison test. And I'm going to give you kind of an informal way of understanding what's going on in the comparison test. Let's talk about the comparison test. Then we're going to come back and use it on that example we just looked at. All right. All right, so we've got an improper integral from a to infinity. Now, if f of x is less than g of x, and g of x, its improper integral converges, then the improper integral of f of x converges. Let's talk about why that is. So here's what's going on. And this is a nice one because we can look at it graphically. All right. Now remember, these are going from some point A. Let's put A on here. Oops. Some point A up to positive infinity. So I'm only going to draw part of it. But basically what's going on, we have two functions. F is always less than G to the left of A. So, and this thing keeps going. So let's say that's our f of x. And in here, does whatever, but it's always bigger. And there's our g of x. So f of x is less than g of x. Let's talk about what this is saying. If the improper integral of g converges, what that's saying is there's a finite amount of area between a and infinity under g. Well, if there's a finite amount of area under g, then there must be a finite amount of area under f. That's what the comparison test is saying, because f's area is less than a known amount of area. Okay, we can, you know, hey, let's say the improper integral for g. Make sure we do the right color. Let's just say, for argument's sake, the improper integral for g. Let's make that of g of x equals 10. You know, we calculated it, we got 10. Then what we know is that because f is less than g, the improper integral of f is less than or equal to 10. So f, got the x. So the improper integral of fx dx converges. Now we cannot say it converges to 10. We can just say it converges. We just know it's less than or equal to 10. It could be 10, probably something small, but that's all we're trying to do is prove convergence or divergence. Okay. The other thing, there's going to be another part to the comparison test, but I want to finish talking about this part first before we go on to the next. So if we're doing the comparison test and the one we know is convergent, G would be the one we know. G would be like that one we converted. We can not converted. The one that we found first, which was 1 to infinity of 1 over x squared. That would be like our G. That's the one we pick. And then we show the one we're comparing is less than to it, then we can show convergence. So we can only use a convergent to show convergence. And we must show that the one we're testing is less than the one we know. It does not work in the reverse. If f were to go above g, and so we lose this, we don't know that f is less than g, but we know g is convergent. Like if f is greater than g and g is convergent, then that is inconclusive. It doesn't tell us anything. Okay? So these are one direction. This is the only thing we can show as far as convergence. Let's do the other one and then I'll take questions. All right. Now, let's say G is the one we know and G is less than F. So I'm going to draw a very similar picture because I want to just, like I said, I want to make this intuitive for you guys so you don't feel like you're trying to memorize some arbitrary rule, because it's not. It comes from a very, very rational place, as does R. But if you can kind of understand the informal argument, That's going to make it easier to remember what you can and can't do. You want to keep that. All right. All right, so once again, we're going from A up to infinity. G is in blue. So this time G is small. So there's our G of X. And then now F is bigger. Does whatever. But it's bigger. Okay, now this is saying if G is known and F is known to be bigger than G, and G diverges, then F diverges. Same basic idea. Basically what this is saying is, hey, we've got an infinite amount of area under G, something we can't calculate, it didn't converge, and F is bigger. So if this is already infinite and F is bigger, it must be also infinite. So if G diverges, then F diverges. We can kind of, set up, this one's a little bit tougher because we wouldn't be using an actual number, but very similar to the one above, I can only use a divergent to test for divergence. And I must show the one I'm testing is bigger than the one that I know. All right, so that's an informal, the informal thinking about the comparison test. Questions about this slide before we look at it in practice? Okay, we're going to do a couple. First one is the one from the slide, which is this guy here. We're going to use the ones that we did to show convergence and divergence. So, all right. Now, how do you choose them? You look at your lead terms. So like this is 1 over x squared as lead terms. So if I'm going to, now it must be one that we know in order to compare. So I'm going to try and compare it to 1 to infinity of 1 over x squared dx, which we know converges. So I'm going to try and show convergence. That means I need to show that this guy on the left is less than or equal to this guy. So here's what we're going to be doing with the comparison test is writing not a formal proof, but a loose proof, 2 to 3 lines. We have to show that what we're saying is true. And what I like to do, the way I like to teach this is to work in reverse. Want to show, so that's WTS. What is it I want to show? Start with that. I want to show, you don't need the integral signs for this. 1 over x squared plus 2x plus 3 is less than or equal to 1 over x squared. What we're doing is we're using this part of the comparison test. This is our G, this is our F, all right? This is the part we have to show, but we know this, we computed it earlier. If I can show this, then I know that this thing must be convergent. This is not enough to completely show it. You need to do a couple of steps. So what we'll do is we start at something very basic. In fact, let's start at this. 1 over x squared, x squared. How does x squared compare to x squared plus 2x plus 3 for x greater than or equal to 1? Which side is bigger for x greater than or equal to 1, left or the right? You can put an L or R in the chat if you want. Which side's bigger as long as we know x is greater than or equal to 1? Yep. Yeah, left, clearly. Now, that may not be true for other values, but again, we only care from 1 to infinity. So we have this. Okay. Well, now what we do is we flip them. So 1 over x squared and 1 over x squared plus 2x plus 3. Here's a little reminder. 1/2 versus 1/3. 1/2 is bigger than 1/3. You flip them. What's bigger now? When you flip the two sides of an inequality, sorry, I was just laughing at John's first. Happens to all of us, John. When you flip the two sides of an inequality, it flips the inequality. We have now what we want to show. All right. And so now we can say the integral from 1 to infinity of 1 over x squared plus 2x plus 3 dx converges by the comparison test. CT, you're going to see I use a lot of acronyms, especially when we're writing proofs. CT, I'm just using for comparison test. All right. We're going to do one, maybe two more examples. Oh, sorry. Yeah, go ahead, John.
Yeah. How exactly did you flip the inequality again?
Going from these here to here. Is that, John, that's the step you're asking about?
Yeah.
Okay. The thing is, in writing proofs, we know where we want to end up. And so I needed a starting place that was really obvious. So basically I said, well, if I compare the denominators, maybe that'll work to get me a comparison of these two fractions. So we do this, we get our inequality. And I know that by taking the reciprocal of both sides, I'm going to get the integrands. Well, this is always true. Whenever you take the reciprocal of both sides of an inequality, it will flip the inequality. So by taking the reciprocal of x squared plus 2x plus 3 and the reciprocal of x squared, that automatically inverts the inequality. And it will always work. And guys, this is going to be something you're going to use a lot when you write up proofs for these problems. Did that help, John?
Yeah, cleared it up a bit.
Okay. Other questions about this one? Like I said, we're going to do a couple more examples. All right. This was in the so I'm putting the link for the handout for today. It was also in the invitation today. So if you already have it, it's the same worksheet. We're going to take a look at this worksheet and do one, maybe two. I'm hoping to have some time for you guys to at least get to try one of these, but we'll see how it goes. All right. Okay. Actually, before we do the worksheet, is there one I want to do? No. Okay. So I've got one that I'm going to do before we do the worksheet. So I'm going to make up one that because I want you to see a divergent one, and then we'll do one more convergent, and then we'll see what kind of time we have left. Okay. All right. Integral from 1 to infinity of cosine of x plus 3 over x dx. All right. So I need to do a comparison test on this. Notice that the x doesn't have an exponent in the denominator. All right. We did one similar to this earlier. We did 1 to infinity of 1 over x dx, and we found that that was divergent. All right. Now remember, for divergence, I can only test for divergence. G is my known one. This is my G. This is, I don't want to do this. This is my g of x from this slide. This is basically my f, okay? So I can only test for divergence, and I must show that f is bigger than g. All right, so I want to show that, you can put them on either side. I want to show that this side is greater than or equal to this side. Okay, this is the last line of our proof, but I like, because you guys don't have a lot of proof writing experience, I want you to start with the last line. Start with what you're trying to show and build to it. All right, so let's start with this. So what is cosine of x always bigger than for x greater than or equal to 1? What is the minimum value of cosine of x? I'll give you a hint. Think about your unit circle. What are sine and cosine trapped between?
0.
Not 0. Think of the graphs, right? So think of a sine or a cosine curve. I drew a sine curve, but cosine
-1, right?
There you go. -1 to 1. Sine and cosine are trapped in between -1 and 1. So we know that cosine of x is always greater than -1. That is a fact. That is something we're going to build from. Then, if we add 3 to both sides, cosine of x, whoa, too many x's, sorry guys. Cosine of x plus 3, well, add 3 to that side, we can add 3 to this side, is greater than or equal to 2. All right, well, let's divide both sides by x. All right, that's great. Well, 2 over x. Well, there's 2 things I want to talk to you about this. Number 1, it's very easy to show that 2 over x is greater than or equal to 1 over x, right? It's double it. The other thing, though, is multiplying an integral by a number does not change whether it's convergent or divergent. So if 1 to infinity of 1 over x dx is divergent, then any number, 2 over x, because that's just double this, is divergent. That's always true. That's a fact. That is something we can use in these proofs. Because, you know, now we can just deal with the 2 over x if we want. Well, hey, 1 over x is divergent, so is 2 over x. Doubling infinity is still infinity. And doubling a finite number is still a finite number. So sometimes, and you'll see it in some of the examples, sometimes it's to our benefit to double or cut in half or something our integral to get this inequality to be the way we want it to be. So we have 2 choices. We can either go with, you know, cosine x plus 3 over x is greater than or equal to 2 over x, because, hey, we know that's divergent. Or we can say it's greater than 1 over x, because 2 over x is greater than 1 over x. So either case, we have shown that our integrand, our f, is greater than something that is divergent. So the integral of 1 to infinity cosine of x plus 3 over x dx diverges by comparison test. Guys, the comparison test is going to take a little bit of getting the hang of. I'm recording everything I'm doing today, so that'll be uploaded. Get some more videos in the lesson. You'll also have some more videos when you go to do the homework. You're not going to have to write out a bunch of proofs for the comparison test. More often than not, you're just going to be filling in the arguments in the homework. on the midterm, it'll be a multiple choice. So it'll say which is the appropriate use of the comparison test. So we just need to know how to use it. But to know how to use, the best way to learn how to use it is to write up some of these proofs. So I am, you're going to want to do that when you work through your homework. Questions about this one? All right. Let's see. I put the worksheet in chat. Let's do one from the worksheet so you can kind of see how this worksheet works. Basically, the way the worksheet works is the left side column, which is 1 through 21, so it actually does go over to the right. Those are all ones that can be calculated. We've done 1 and 2. All of these are ones that you guys can calculate. Some of them use U sub, some of them use integration by parts to find the antiderivative. But remember, all you're doing is taking the improper integral, making it a proper integral, taking the antiderivative using the fundamental theorem, and then taking the limit. All right. Let's do one, and then on the right side is for comparison purposes. So you would choose one from the left side because you do the left side, you know if they're convergent or divergent. Then you can use those to test ones on the right. So let's see how that would work. And I think it's worth going through one more example. And we hopefully will have a little bit of time for breakout rooms, but if not, that's okay. I think this is worth going through. Let's do number 12. 12 is a cool one on the left-hand side. Now, first thing I'll point out about number 12. If all we had to do was show whether it's convergent or divergent, this would be a great one to use the comparison test on because it's really easy to show this is less than 1 over x squared. All right. But I want to actually count. This is one we can actually calculate. So let's do that. And then we'll see how we can use it in a comparison with one on the right-hand side. All right. So first thing we do, limit as b goes to infinity of 1 to b, 1 over x squared plus 1 dx. We're going to do the antiderivative there. This is arctan. This is why I'm choosing this one. It's kind of, oops, sorry, we've taken the antiderivative. It's arctan. Arctan is a really cool one going to infinity. So I just want to take a look at it from 1 to b. Limit as b goes to infinity of arctan of b minus arctan of 1. Okay, so here's this guy we're going to have to do the limit on. Arctan of 1, remember what that means? That's saying tangent of what angle equals 1. Well, tangent is sine over cosine, so this is the angle where sine and cosine are the same. So that's at pi over 4. So arctan of 1 is pi over 4. Now, again, you're not going to have to remember a whole bunch of truth in this class, but it does come up, and I just want you to see how you can find this stuff. Let's graph arctan. And let's get back into a normal window. Now, so let's just do negative 10 to 10 and negative 10 to 10. All right, get rid of this. And we're going to do y equals arctan of x. No y. All right. Now, a couple things. Number one, we had to figure out what arctan of 1 is. There's 1 right there. Desmos actually gives you. Okay, like I said, most of the time you're not going to have to memorize many. Now, the other thing is, if I zoom out, this is a graph that has two horizontal asymptotes. And if you don't remember where those are, this is why part of the reason we're looking at this one, you can put them in. So y equals pi over 2, there's a horizontal asymptote. And y equals negative pi over 2. Arctan is a really cool graph because we don't have a lot of graphs that have two horizontal asymptotes. Our logistic functions do. Oh gosh, Gina, I just saw your question in there. I totally missed it. Mark, thank you for answering it. Sorry guys, I sometimes miss things in chat. All right, so what we see is as we go to infinity, arctan goes to pi over 2. So we get pi over 2 minus pi over 4. Finding a common denominator, that's 2 pi over 4 minus pi over 4, which is pi over 4. So this guy converges to pi over 4. Again, when we can calculate it, we know that it converges to that number. When we use the comparison test, all we're showing is that it converges or diverges. All right, so that's how we could show that one converges. Questions about that before we go find one to compare it to? Okay. So we need one to compare it to. Remember, you go off the lead term. So we're looking for something that has either a 1 in the numerator and x squared in the denominator, or reduces to 1 over x squared. In looking over here, 3 is a good option. Might be able to do 8 and 9. So those would be ones we could look at too if we wanted to do a comparison. So 3, 8, and 9 would be good for this one, or even 1 over x squared, whichever one we want to use. So we're going to do 3 now from the right-hand column. And what we want to see is if we can show that 1 to infinity of 1 over x squared plus x dx. We want to show, if we're going to compare to this one, we want to show convergence. All right. We already showed this converges. So we need to show, or we want to show, that 1 over x squared plus x is less than or equal to 1 over x squared plus 1. We're always going to have at least one line. So we'll work in reverse. Flip both fractions. So x squared plus x squared plus 1. And maybe we even go one step further. It's really easy to compare x squared to x squared for x greater than or equal to 1. That's kind of a weird one, actually, since they're equal. But we could do it. Well, yeah, x squared is equal to x squared for x greater than or equal to 1. Well, what about adding x versus adding 1? And again, this is for x greater than or equal to 1. Which side is greater here, the left hand or the right hand side? What do you guys think? And actually, what would be a really cool first step on this one? Let's not compare x squared to x squared. Let's make a really obvious comparison. X versus 1, right? And again, this is only for x greater than or equal to 1. We can look at a graph of them. You know, here's x equals 1. Well, the graph of 1 is just a horizontal line. The graph of y equals x. So clearly, we have the case where f lies below g. So x, oops, I almost drew that backwards. So x is clearly greater than or equal to 1 for x greater than or equal to 1. It's actually a redundant statement, right? It's the same thing. Well, then what we do is we basically add x squared to both sides. So kind of similar to the way we did the last one. Adding both x squared to both sides, we add the same thing to both sides. It does not change the inequality. So x squared plus x is greater than or equal to x squared plus 1. Then we know that taking the reciprocal of both sides flips the inequality. We get the inequality we want to show. So the integral from 1 to infinity of 1 over x squared plus x dx converges, because we compared it to a convergent, by comparison test. So that's how the worksheet is intended to be used. We may not have time for it today. We'll see what we want to do next. But first, questions about this problem. So what we did is we calculated one, found it was convergent. Then we used it in our comparison test to prove that the other one was convergent. And again, like we said, in the first part, we can show what it converges to. The second one, all we can say is that it converges. We'd have to use some other method to see what it converges to, some numerical method. Okay, questions about either of these? All right, let's see, what time is it? 6:07. Talk a little bit again. You know, I think we have enough time for you guys to calculate an improper integral. So we'll do breakout rooms just for about 15 minutes. So in your groups, pick one of the ones on the left-hand side that I didn't do. So we did 1, 2, and 12. Pick any of the other ones to try, just to practice calculating an improper integral. I don't know that you'll have time to do the comparison test, but just to try one, and that'd be what. So you can try one. You have something to post to see if you have any questions. If you do want to try a comparison test, feel free. Like I said, we're going to go to about 6:25, but I want to save a few minutes at the end just to mention just a couple of things. Actually, probably even a little. We can probably go a little later than 6:25. All right, so let me get you guys in the groups. Let me know if you have any questions.